Good evening, ladies and gentlemen. Welcome to the Royal Society of Edinburgh, Scotland's National Academy. My name is Anne Glover and I'm the president of the RSE. And I've got one or two housekeeping things to mention to you just prior to my introduction of Professor Hinton. So first thing is, there is no scheduled fire alarm this evening. So should an alarm sound, then please leave the room as fast as you're able. And I'm also speaking to people in an overspill room because this is a sold-out gig. So people in the overspill room will also see fire alarm exit signs on the wall. Please leave as quickly as you're able in this room, straight out the back. And when you get out onto George Street, turn right and move along the street out till outside the Dome, big building with pillars outside. So no fire alarm. The second one is that this lecture this evening is live streamed on our YouTube channel, and there will also be photographs taken. And if you're unhappy about photographs being taken, then please see a member of staff and they will speak to you about that. I think now, is there anything else formal for me to say? I think probably not. So now the pleasure of the evening for me, which is to introduce Professor Geoffrey Hinton. Now, Professor Hinton is known as the godfather of deep learning, and it's my enormous pleasure. I never thought in my life I would get to introduce the godfather of anything. So this is a special moment for me as well as for all of you. And the other thing that I have to say that is a complete delight is just looking at the audience. We have a very young audience in this evening, so please come again to our other lectures. But it's very refreshing than we usually have at the RSE lectures. I think I said that tactfully. And also a real joy, and again this is a first for me, is to have people, and I'm kind of loitering purposefully as Professor Hinton was coming out after having a cup of tea to get a selfie with him. That's just the best. So let me give then a brief introduction, and really I don't have to for this audience, but Professor Hinton got his PhD at Edinburgh in artificial intelligence, I guess, in 1978, and then moved from there to Carnegie Mellon University, and was there for a number of years before moving to Toronto, and he's still in Toronto at the moment as the Chief Scientific Advisor of the Vector Institute, but is also a Google Engineering Fellow. Now, the importance of the research and knowledge generated by Professor Hinton is very hard to crystallize and to just try and summarize in a sentence or two. But because I'm a simple molecular biologist, and I was looking at some of the things that Professor Hinton has done and has been awarded so many prizes, including the IEEE RSE James Clerk Maxwell Prize in 2016 rather. But I was thinking about how has the work that Geoffrey Hinton has done affected my life. And I was thinking something actually very simple, such as voice recognition, because I am old enough to remember having a computer that you used to have to sit down and do 2 or 3 hour tutorials with in order to try and get the computer just to understand some simple things that you were trying to say. And yet we all know now that voice recognition is incredibly simple. But the whole idea that you can get machines to learn in the same way as human brains learn, and trying to think about the parallels between them, or how understanding of human brain and neural networks can affect how machines learn, and what that can do for us is quite something. And for me, it paints both an incredibly exciting future and also a really challenging one in how, when you have that ability, what you can do with it. So that's enough of an introduction to me, and I'd now like you to welcome, let's just say, the Godfather.
The first 40 minutes or so of this talk are going to be mainly introductory and historical. And so if you do deep learning, wake up after about 40 minutes and there'll be some new stuff. Okay. And also, if you do AI, this is oversimplified. So, yeah. So basically, there were two paradigms for artificial intelligence from the early days, from the late 1940s or early 50s. There was the approach that I think of as the logic-inspired approach, where the essence of intelligence was manipulating symbolic expressions using symbolic rules. And the sort of core problem was reasoning. How can we get computers to do reasoning? And then there was a different approach, where the essence of intelligence was learning the strengths of connections in a neural network. And those people focused more on learning and perception than on reasoning. They thought of reasoning as something that comes very late biologically, and we should focus on things that come earlier. These two different camps had two very different views of internal representations. So for symbolic AI, internal representations were some kind of symbolic expression, and you could actually give these to a computer if you got the right language to express them in. You could tell the computer how to represent things. And the computer could derive new representations by applying rules to representations you've given it. Whereas for neural net people, the internal representations were nothing like language. Language was just a way of communicating, but what went on inside was nothing like language. They were large vectors of neural activity that had direct causal effects on other vectors. And these vectors were learned from data, and the individual features in these vectors were what made them worth having, gave them meaning. So corresponding to that, there's two ways to make a computer do what you want, one of which I've called intelligent design, which sort of shows slightly where my prejudices are. You figure out consciously exactly how you would do something like sorting a list, and then you tell the computer exactly how to do what you figured out consciously, and it does it. That's called programming. And the other, you just show it lots of examples, and of course you write a program, but it's just one program, you hope, and it's the same program sort of independent of the task, and now you get to do particular things by showing it different sets of examples. So here's a kind of classic example of the kind of thing we'd like a computer to do that's hard to program. You imagine the pixel intensities of those colored pixels on the left, and so you have maybe 3 million numbers. And from those 3 million numbers, you want to get a string of words that describes what's going on in the picture. And you could try writing a program to do that, but it's very difficult. Or you could try just training it. That's also very difficult. But if you use enough computation and you break it up into a few stages, you can now do that. So the central question was, everybody would agree that a large neural network with nonlinear neurons and multiple layers and millions of weights is a very powerful computing device that could do all sorts of things. But how do you get it to do those things? And the question is, just by showing it examples, or do you need to put in lots of prior knowledge? And I think it was perfectly reasonable for people to feel that it's unlikely to work. So there's an obvious learning algorithm, which is Turing. Turing was very interesting. He obviously knew a little bit about logic and stuff. But he also was actually in the other camp. He thought when it comes to understanding the brain, we should have what he called unorganized machines, and we should have connections that just learn their strengths by reinforcement learning. Selfridge in the early days of AI believed the same thing, but it's extremely inefficient. I'll explain why later. In the 1960s, Rosenblatt came up with an efficient algorithm. So if you give it the features, so you take the data, extract some features, it just decides how to weight these features to make a decision. And it was an efficient learning algorithm that could do some things, but then Minsky and Papert sort of totally destroyed it in 1969 by showing there were strong limitations on what it could do. Like it couldn't even compute if two input lines had the same value, which seems a bit primitive. And they implied that if you had deeper networks, it wouldn't get you any further. They would also be very limited, mainly because nobody could see how to learn these deeper networks. And so that led to the first neural network winter, which is when I decided to come to Edinburgh and do research on neural networks. I think I arrived about the observation we should be doing symbolic AI. In the 1980s, the backpropagation procedure came along, and I will explain the backpropagation procedure for the less young members of the audience. Did I say that right? And the point about backpropagation was it allowed neural networks to design their own features. And so you could have multiple layers of features. And early on, we showed that it could do some quite impressive things. On small toy examples, you could give it strings of words and get it to try and predict the next word by first turning each word into a vector, and then from these vectors try and predict the next word. And it learned interesting vector representations of words that captured their meaning. So similar words would have similar vectors. And we hoped that it would solve problems like speech recognition and shape recognition. And it did do simple versions of those, but it was basically a disappointment. So first of all, I'm going to explain to you how backpropagation works. Just an overview of it. So the idea is we want to understand what you can do with a big network of neurons if you can learn connection strengths. And we're going to idealize the neurons. Real neuroscientists don't like this, but we're going to idealize them a lot. We're going to say, let's think of a neuron as something that has incoming lines, it has connection strengths on these lines, so it takes the activity on a line, multiplies it by the connection strength, adds all that up, and then decides it on output by putting that sum through some nonlinear function. And a nice simple nonlinear function to use is this one here, where if the sum is below threshold, the sum of this activity times this weight and this activity times this weight and so on, if it's below the threshold, you get 0 out. It's very important to have a region where you can kind of hide things. This is the sort of rug that you can sweep things you want to ignore under. So changes in the input, if you're below here, don't change the output. So it's capable of ignoring things. Here, changes in the input will change the output, and it's just linear. So that's a very simple kind of neuron, and it turns out these work very well. Then we could connect those together into a multi-layer network. And the issue is, can you learn weights like these ones and these ones? Perceptrons could learn these weights, the weights from feature detectors to the outputs, if you tell it what the right answer is, but they couldn't learn these weights here. This is just a feed-forward neural net, and we call these hidden layers. And there's two ways to train nets like that. The supervised training, where you tell it what the right answer is for each input, and it tries to change the weight so that it gets the right answer or gets closer to the right answer. And there's unsupervised training, which is much more like most of the learning people do, where it somehow learns without being told what the answer is. And maybe it's learning to predict what comes next. You could think of that as an answer. Or maybe it's learning just to extract structure from the input. And that's coming back into fashion now. So I'll start off by explaining supervised training. So imagine we had a network like this and we wanted to learn all these weights. There's an algorithm that sort of everybody who knows about evolution thinks of. And it's a very sensible algorithm. It's just hugely inefficient. What you do is you put random weights in here, and then you look at one of the weights, this one, and you say, should I make it a bit bigger or a bit smaller? So you try a bit bigger. And you take a sort of sample of training examples. You put all the examples in the sample through, and you measure how close you get to the right answer. Maybe you want to distinguish cats from dogs, and so you put in a cat and see, is it saying more cat than dog? And then you change this weight slightly and say, does that make it better, more cat, or does it make it less cat? And over this little sample of training examples, you see if increasing this weight helps. If it helps, you increase the weight. If it hurts, maybe you decrease the weight. But only by a little bit. And then you go around to the next weight. And if there's 1 million weights, this is going to take a long time, because for each weight you have to take all these examples and put them through and see whether it helps. So the backpropagation algorithm is basically doing the same thing, but just much more efficiently. That is, it's tinkering with the weights to make the net give better answers. But instead of perturbing a weight and measuring the effect on the answer, which is what evolution has to do, because in evolution, if you perturb a gene, you don't have complete control of the environment. You don't know everything that's going to happen, so you can predict exactly the effects of perturbing that gene. But in a neural net, you know exactly when you perturb a weight what's going to happen to the output, because all that's determined by the other weights. So it's very different from evolution. You don't have to change it and see what happens. You can compute what would happen if you changed it, because everything depends on the weights that are in the neural net. So we're now going to compute how the error of the net would change as we change each weight. And we can do that for all the weights in parallel using calculus. And with 1 million weights, it's 1 million times more efficient. So it's practical. And so you take your net, you want to learn all these weights, you take a training example, you put it forwards through the net, you compare the answer with the correct answer, then you send a signal backwards, which is using the chain rule for derivatives, and basically computing for every weight in the network how, if I were to increase that weight a tiny bit, what would happen to the error in the answer, the discrepancy between the actual answer and the correct answer. And you do that for a little batch of training examples. And for that batch of training examples, you now have the gradient. That is, you know whether changing this weight will help or hurt. And then you change every weight in parallel by a little bit, and then you get another batch of examples. And so backpropagation is the algorithm for a single training example, how changing this weight would help with that training example. And that's how you get the gradient. And then you use something called stochastic gradient descent. So if you were normally doing optimization, you would say, well, I need to take all of my training examples, compute for all of my training examples how changing this weight would help or hurt, and then change in the right direction. But if you've got a lot of training examples, like a whole lifetime's worth, you don't want to live your whole life and then on the very last day decide to update the weights. Actually, that might be quite quick. So it turns out you can take a small sample of training examples, update the weights based on the gradient you computed there, which might be wrong because it might be an atypical sample, then take another small sample, update the weights again. And if you did them in the wrong direction, it'll sort of get cancelled by other examples, and it works. And a priori, it's kind of quite surprising how well it works. Initially, people thought you'd have to use all the data, and that would be slow. Then they thought, okay, we can use mini batches, but we'll get stuck in local optima, and that'll be a problem. Well, in practice, it's not a problem. That is, you don't get the global optimum, but you do get a solution that's good enough. And then people said, well, you know, fancy second-order optimization methods are much better than dumb methods like gradient descent, stochastic gradient descent, so we should be using those. And it turns out a huge amount of effort has gone into trying to make those work, and they never work significantly better. They never work enough better to be worth the effort. So in practice, all you need to do is use momentum, which says, when I change the weights a bit, as well as changing the weights based on the gradient I just computed, remember how I last changed the weights and change them a bit in that direction too. So you've just got sort of momentum in changing these weights. And the other trick you need to use is, if you've got a connection that keeps getting big gradients, use a smaller learning rate. That is, multiply those gradients by a small number so it doesn't kind of thrash around. And those two tricks is the state of the art, which is sort of embarrassing. Hundreds of journal papers have been written on how to do this, and those two tricks is as good as anything. However, in the 1990s, there was a big disappointment, which is people like me went around saying, okay, we got it, now we can do anything. And it turned out, once you have multiple layers, it was quite hard to train these networks. And we didn't know why. If we'd said at the time, it's because we don't have big enough computers and we don't have enough data, people would have said, yeah, right. But that was part of the reason. Another part of the reason, which is sort of embarrassing, is we didn't initialize them right. So on modest-sized data sets in the 1990s, other methods, things like support vector machines and Gaussian processes, worked better than backpropagation. And in the machine learning community, people abandoned neural nets again. Not in psychology. In psychology, they kept playing with them. And so we got a second AI winter, or neural net winter. The terminology is very confusing because I think there's AI, and that's symbolic AI, and then there's neural nets, which is this crazy stuff I do. And as soon as the crazy stuff started working, people started calling it AI, which was very confusing. So, in the 1990s, symbolic AI researchers sort of basically claimed they were vindicated, and okay, so you can learn toy problems like this, but great big neural networks with many layers and billions of weights, you're never going to learn them without injecting a lot of knowledge. It's just crazy to think. It's silly to think you can learn everything just from data. It's sort of wishful thinking, romantic wishful thinking. And that wasn't an implausible view. I actually went to the same high school as John Cleese, so I just thought I'd put some really silly theories. So here's a really silly theory, that the continents used to all be connected together and they sort of drifted apart. Geologists laughed at that one for 40 years. Then great big neural nets, starting with random weights, can just learn from data, and they'll be able to do things like machine translation without ever having any knowledge put in. Well, that seemed equally crazy, probably more crazy. There's a theory that if you take a natural remedy and you dilute it, it gets more potent. That theory actually is crazy, but don't tell the NHS because it's very cheap. The quote at the top is taken from a geologist. This was their view in the 1940s and 50s of continental drift, which is it was very important to keep it out of the textbooks because it would just sort of encumber the literature and befog the mind of students. David Attenborough has a wonderful quote about what happened when he asked a geologist, but what about continental drift? He was kind of severely told off for being so stupid. And so I've got one slide, so indulge me. I've got one slide of resentful we told you so's, okay? But just one, I focused it all on one slide. So in 2007, the NIPS Programme Committee rejected a paper by me and Russ Salakudinov. And I asked them, why did you reject this paper? I thought it was a good paper. You may have had the same experience of a conference rejects your paper and you ask someone on the programme committee, how come you accept all the other rubbish papers and you rejected my one? And my friend on the programme committee said, well, we already accepted a paper on deep learning and we couldn't have two. Okay. In 2009, it was already beginning to work well by then, Yoshio Bengio got a review of a paper sent to ICML. The paper was rejected, but one of the reviewers added that he shouldn't have even sent it to ICML because papers on neural nets had no place at ICML. That's the International Conference on Machine Learning. And then the computer vision and pattern recognition. So these are the top conferences in their areas. Rejected paper by Yann LeCun. That was the most gratuitous because he had a system that worked better than the state of the art at segmenting images. And the paper got rejected. And the reviewer said, the reason we're rejecting this is because it tells us nothing about computer vision. It's all learned. Now, the reviewer had obviously, like most of the computer vision field, had decided on how you do computer vision, which is you figure out what computations are required, and then you figure out how to implement them, and off you go. And if someone just says, I learned a whole bunch of parameters and it did it, well, that's not progress. That's not telling you what computations you should be doing or how you're going to implement them. The reviewer didn't sort of have the wit to see, maybe it was telling him something that was just all learned. That wasn't in his repertoire of ways of doing computer vision. Okay, that's enough of that. So between 2005 and 2009, researchers in Canada, well, we count Yann as being in Canada because he's French and in America. We made several technical advances that made backpropagation work better. And the big picture is that technical details aren't really important. The main message is that if you do backpropagation in big networks with a lot of data, with a lot of computation, so you need things like GPUs, it now works really well. However, since I'm a researcher, I'm going to go into the technical details. So some of the tricks that made it work better were unsupervised pre-training. So initially, in the old days, when we tried training deep networks, they didn't work. They would never really get off the ground. They were very, very hard to train. And it turned out they could be made much easier to train by, instead of trying to train the whole network to produce the right answer, you would take your input, let's say pixels, and you would learn a layer of features that were good at reconstructing the pixels. So you say convert the pixels into some feature activities such that from these feature activities we can reconstruct the pixels. I'll talk more about unsupervised training later. And having learned those features, unsupervised, you say, now let's take those vectors of activities of features, treat those as data, and now let's learn some more features that are good at reconstructing those feature activity vectors. And we can learn lots of layers of features like that, all without being told any labels. Of course, we don't know that we're learning anything sensible, but we are learning to find correlations in the data, and maybe that's what structure is. And it turned out that if you do a few layers of that, and then you turn on backpropagation, you put your class labels on top, and then you apply backpropagation, it works much better. And what's more, it gets a big, big sensible gradient to begin with. And so that helped a lot, particularly if you don't have much training data, that helps. Then there was another trick that helped, which is called dropout. So suppose you have two units that are trying to predict an answer, like whether it's a cat or not. And suppose one unit always overpredicts. Let's suppose they're trying to predict a real number, like somebody's height. And one unit always predicts 7 feet, and the other unit always predicts 5 feet, and most people are 6 feet. Then between them, they'll do okay. When you average their predictions, you'll do fine. And so the units can get away with giving the wrong answer as long as their errors are cancelled out by other units. But if one of those units sometimes doesn't show up for work, then the guy that says 7 feet is going to make a big mistake. And so if you just randomly leave out units so that you can't actually rely on anybody else, you have to become a bit more independent. And really what you need to do is do something that's useful marginally, given what other people are doing, but not knowing which other people are doing it. And it turns out that makes the neural networks generalize much better. And then there was rectified linear units, which I already explained. Before that, we spent about 30 years using units that had an input-output function that was a sigmoid. And they don't work as well as rectified linear units. And I think we should sort of take a lesson from that. We spent 30 units using one simple nonlinearity when another one was better. So what are we doing wrong now? And should we maybe do it wrong for less than 30 years? So the first real good application of this stuff was, or the first commercially relevant application on a big scale, was for speech recognition. In speech recognition, it used to be, there's a front end that does acoustic modeling. What acoustic modeling means is you take something like a spectrogram and you ask for the middle frame of the spectrogram, which piece of which phoneme is the person trying to express? So we took 11 frames of coefficients describing the sound wave. And then we just put in lots of layers of hidden units. When I say we, I went away for the summer and 2 of my graduate students used some techniques that I had some role in developing and actually beat the state of the art on speech recognition on a fairly small database called TIMIT. But the point is it was a different technique and it works noticeably better than highly tuned techniques from IBM and other places. And so it could say which piece of which phoneme people were saying. Then there's the rest of the speech recognition system that then takes all those bets about which piece of which phoneme and strings it all together for the most plausible utterance. And of course the speech people said, yeah, okay, so you can do the front end, but you'll never replace the hidden Markov models and the language models and all that stuff. Yeah, right. So that once they got that model working, people at Microsoft, a researcher called Lee Deng at Microsoft, realized very early that this is going to wipe out the state of the existing technology. And different graduate students from my group went off to different groups, to Microsoft and IBM and Google. Navdeep Jaitley went off to Google in 2011. He wanted to go to RIM, which made the BlackBerry. Is in Canada, and we developed the technology in Canada, and we tried to give it to a Canadian company. And the Canadian company said, we're not interested in speech recognition. That's the problem with being an academic in Canada and being evaluated by whether you have industrial impact. So he went to Google, and Google then did a lot of nice engineering to make it efficient, and it came out in the Android in 2012, and that was a big leap in the quality of speech recognition, and then all the other companies copied it. Now all of the best speech recognition systems use neural nets, but not that kind of neural net anymore. They're beginning to use end-to-end neural nets that just turn sound waves into characters in a transcription, or even sound waves into sound waves in another language. The next big thing that happened that I know about was in 2012, there was a public competition. It had run for several years, called the ImageNet competition, where someone called Fei-Fei Li put a lot of work into collecting a big database of images. And the point is, neural nets couldn't show what they could do until somebody collected a big database, and it was a lot of work. So she got millions of, and in the ImageNet competition, there were about 1 million training images of 1,000 different classes. And the images were labeled not necessarily reliably, so there might be a Dalmatian and a bowl of cherries, and you didn't know whether the label would be cherry or Dalmatian. So you could make 5 guesses, and it was counted as right if you got the correct label in your top 5 guesses. That was the standard back then. And many of the best computer vision groups in the world tried to show that their technique was the best. And what happened was that the standard computer vision of the time, of 2012, was asymptoting at about 25% error. And 2 graduate students at Toronto, Alex Krzyzewski and Ilya Sutskova, with a little bit of help and encouragement from me. Actually, I had mainly managerial input to that. Alex Krzyzewski is an incredibly good programmer. And he had to write a depth oral, and he doesn't like writing. Depth orals are like quals for your PhD. And I told him, every time you reduce the error rate by 1%, he could put off writing the depth oral by a week. And he put off writing the depth oral by months and months. So, this surprised the computer vision community that we did 10% better than their best systems, almost half their error rate. And to be fair to the computer vision community, up to that point, they'd been saying, Papa, these neural networks, they're only going to work for simple images. They're never going to work for real images. When that happened, the leaders of the computer vision community, like Jitendra Malik and Andrew Zisserman, said, hey, wow, these things actually work. And they started using them. And pretty soon they were using them better than we were. So what happened was actually right, which is they were very skeptical of this weird technique, and then when it worked, they changed their mind. Now, these neural nets are down to around 3%, and they're better than people on that data set, not in general. The last application I talk about is machine translation. And in 2014, Ilya Sutskever, who's missing his T, thought of a new way of doing machine translation that sounded crazy, which is you take the words in one language, and Kwok Lee was also involved in thinking of it. Take the words in one language, and use a recurrent neural network, which I haven't explained, to turn that string of words into a big vector. And that big vector is the meaning of the sentence. And then you give that big vector to another network, and the big vector now has to produce the sentence that has the same meaning in another language. So this vector I called a thought vector, because it's the dumb way to do machine translation, right? You listen to what the person says, you figure out what it means, and then you say that in the other language. And it actually worked. Initially it worked about as well as existing machine translation methods. But pretty soon it worked considerably better. So the thing that made it work a lot better was using soft attention, which is sort of obvious. If you want to translate from one language to another, as you're say from English to French, as you're producing the French, you want to look back at the relative bit of the English sentence and let that influence you. But of course, it's hard to know which bit's relevant. So they had a neural network kind of learn which bits might be relevant and which bits were worth attending to. And that made it work a lot better. And since then, people have reintroduced the idea of unsupervised pre-training, and that's made these things work even better. And so in unsupervised pre-training, what you're going to do is you're going to, instead of trying to translate from one language to another, you're just going to take a string of words in one language, and you're going to blank out one or two of the words. Now they're blanking out little combinations of words, but to begin with, they're blank out a word here and a word there. And now you're going to try and reconstruct the blanked out words by using the other words. So that's going to force you to capture information about what the words around a word tell you about what that word must mean. So if I say something like, she scrommed him with the frying pan, you've never heard the word scrommed before. You know it's a verb because of the syntax. And pretty much everybody thinks that it's sort of, he made a politically incorrect remark and she hit him over the head with the frying pan, or something, right? Now it could be she impressed him with her cooking, that's a possible meaning, but you have a strong idea of what scrommed means just from that one sentence, okay? And so there's things called transformers that can be trained to get very good representations of the meanings of the words by trying to get words to disambiguate the neighboring words. So standard neural nets take a product of activities times weights. So there's activities on the input lines and there's weights on the connections. You multiply them together and add them up, and that determines the output of a neuron. But that's not going to compute various things. It's not good at computing whether two input lines have the same activity, for example. There's something else you could do, which is take the product of two activity vectors. If you do that, you're much more sensitive to covariances. And if you look at these images here, let's suppose that the middle image is the best one. I claim that the left image is worse than the right image. Even though square eyes are worse than round eyes, there's something more important than square eyes and round eyes, which is your eyes being the same as each other. Okay, and the right image has the property the eyes are the same, and that's a covariance property. You see the same if I made the eyes different colors too. Maybe blue is okay, maybe brown's okay, but they should be the same. Okay, so transformers are all about covariances. And if we made a normal neural net that took words and gave you many levels of representation of those words, kept re-representing the word by using contextual information, that would be a convolutional neural net that would use the words around it to change the representation of that word. And you could keep going like that and learn representations of words that were disambiguated by their context. And it would look something like this. That would be the sort of convolutional way of doing it. Now, transformers are going to do something a bit more complicated. What are transformers going to do? Notice the word up here is the same as the, but we don't have direct connections anymore. What we do is we train this network just by backpropagating derivatives of how well it reconstructs. So it learns to turn this word vector into a query, a key, and a value. So maybe this is the word vector for the word may. And so you see the word may. Let's suppose we don't have capitals. You see the word may, and it could mean the month, or it could mean the modal, or it could mean the prime minister. And you don't know which it is. But the context will tell you. If over here there's the word June, then this is very probably, it means the month. And so what this word may learns to do is create a query vector, and a key vector and a value vector. And this query vector then gets compared with the key vectors that all the other words have created. So this might be June here, and it might create a key that says sort of I'm a month. And this query vector might say I'm looking for months, or part of the query vector might say I'm looking for months. And so if you get a good match, then you'll get input from the value, and the value vector here might say activate the things that mean month in here. So if this was June, you might get a representation here that's the sort of month version of May. If this was Prime Minister, let's suppose it's all one word, then you might get a representation that activates the politician here, and so on. This is something of a simplification, but this is the basic idea, that instead of allowing things to have direct effects, we're going to get things, each word is going to create a query, and then we're going to attend to some things more than others. We're going to attend to things where the key matches our query. And how much we attend to things, overall, the strengths of these inputs are going to be normalized to 1. And we're going to proportionally say, if you get a good scalar product of the key with the query, you exponentiate that to make things sharper, and then the amount of input you get from that value is proportional to that product. So when it matches, pay attention to it. If it doesn't match, don't pay attention to it. So that's called self-attention, and that's how transformers work. That's a quick introduction to how transformers work. And transformers can do amazing things. So they're very good at machine translation. They're also very good at language modeling. So OpenAI recently did, Inge Sutskever, who was the guy who did ImageNet, recently used a method developed at Google called BERT, which was using transformers to learn word embeddings, using unsupervised learning. And they used that in a language model where you're trying to predict the next word. It's actually word fragments. So they have 32,000 fragments. And so there'll be things like un and ing, and also small words like the. And they'll break up English, for example, into these fragments, and then they'll try and predict the next fragment from a string of fragments. But the initial embeddings they used for the words were designed by BERT. And what they'll do is make a probability distribution over all the fragments that might come next. So I'm going to assume these fragments are words because it's easier to talk about. So they make a probability distribution over the words that might come next. And if there's, for example, a probability of 1 in 100 that cat comes next, according to the model, then what you're going to do is, after you've trained the model, you want to see what it believes. So you give it some introductory string, and you say, what do you think comes next? And it'll give you a distribution. You pick from that distribution. If it says there's a chance of 1 in 100 it's cat, 1 time in 100 you pick cat. And if it says there's a chance of 1 in 2 it's the, 1 time in 2. And then you tell it, after you pick from its distribution, hey, you were right. What do you think comes next? It's quite good doing this with people. If you just let them rabbit on, you can discover what they really believe. You just keep agreeing with them, and they'll get more and more racist. So not all people. just the people you see on the news. So you keep telling it guessed right, and that way you can get it to produce a whole story. And what's amazing is, if you train this thing on billions of words of text, and you train a model that has 1.5 billion parameters, so that's quite a big model now, 1.5 billion. It's tiny compared with our brain. 1.5 billion is 1.5 cubic millimeters of mouse cortex, has 1.5 billion synapses in it. So we're talking about a model that's about the same size as one voxel in a brain scan. Okay, it's tiny compared with the brain, which suggests that the brain maybe isn't using backpropagation, because otherwise we'd be much smarter. So they gave it some initial text where, in this shocking finding, I'll let you read it, and the initial text, obviously there's something weird going on that needs explaining, and they let it now carry on and produce more text. And this text, they could check back in the training data and see that this text wasn't in the training data. And so it made this stuff up, right? And it made up Dr. Jorge Perez, an evolution biologist. There is no Dr. Jorge Perez at the University of La Paz. I'm not even sure this is University of La Paz. It probably is, but he's not there anyway. It just made him up. And it's going to keep talking, and eventually it's going to get around to explaining what really happened, and it's going to explain it much the way Trump explains things. So it sort of makes stuff up, and they were astonished to see the unicorn herd. And then it returns to the kind of topic, which is, you know, while examining these bizarre creatures, the scientists discovered they spoke some fairly regular English. Perez said they had some kind of language. Like most of us, he wasn't quite clear about the difference between a dialect and a dialectic. And since he was from Bolivia, I guess, he assumed this stuff must have come from Argentina. And we now get magic realism coming in. So they were a lost race of people who lived before the arrivals of humans. That's a bit dodgy. And I love this last bit. This is exactly like a Trump. You know how Trump says many people believe. So in South America, such incidents seem to be quite common, of unicorns breeding with the people who were there before humans. And in the end, he gets around to saying, you know, if you really want to know, you need to do a DNA test. And then the last bit isn't quite so good. Now, this is cherry-picked, so this is one of the better things, but it's long, right? I find it amazing that it can produce this stuff that's sort of vaguely on topic and make so much sense just from looking at strings of word fragments. It's not grounded at all. It's very hard to know how much it really understands. Like, I'm going to do a little experiment on you. Yeah, I've just got time. What you have to do is you have to shout out the answer, and you're going to get rewarded for how quickly you shout, not for whether the answer's right. Okay? So the person who shouts first gets the prize. After I finish the question. This is called debugging, I guess, yes. After I finish the question, you have to shout out something that might plausibly be the answer, but isn't necessarily the right answer. What do cows drink? Right. Most people say milk, right? That's the first thing that comes to mind. And they think, wait a minute, most cows don't drink milk. Right? And that's a kind of reasoning we're very good at. You know, there's cows, and there's drinking, and you drink milk, and milk's related to cows. So it's sort of association. And the real question is this thing just doing massive amounts of that kind of sort of associationist reasoning, or does it understand a bit more than that? And I didn't really know the answer. But I think most human reasoning isn't at all like the reasoning that old-fashioned AI people were trying to model, which was sort of proper logical reasoning. Most of the reasoning we do is just intuitive reasoning. It's sort of instant. There's not intermediate steps. Now, of course, you can make your intuitive reasoning better by using training signals you get from doing intermediate steps. But most of the reasoning you do is fairly instant, and it's reasoning by analogy, and it's reasoning by making lots of analogies in parallel, I believe. So, for example, here's something that's difficult to answer by logic. If I say, you've got to agree to one of the following two propositions, and which is better? All cats are male and all dogs are female, or all cats are female and all dogs are male? Well, it's just obvious to anybody in our culture that cats are female and dogs are male. Little children will tell you that, cats are female and dogs are male. It's in our language, and it's because sort of cats are subtle and dogs are big and noisy and chase cats. It's in the feature vectors, right? The feature vectors you have for dogs and cats sort of map onto the feature vectors for men and women, and it's quite clear which way around the similarities go. That's not logical reasoning. That's just these massive analogies going on in parallel. And of course, logical reasoning is relevant to making your intuitive reasoning better. So just as in something like AlphaGo, you've got neural nets that are intuitive that say, this might be a good move to try, or that looks like a good position. That's done without sequential reasoning by a neural net, just multi-layer neural net. But then there's Monte Carlo rollout, where you say, well, if I go here and he goes there, and I go here and he goes there, and that can be used to improve the intuitions. So you do need both. But you're not going to be able to get good reasoning unless you've got the intuitions to guide the reasoning. So that's my current view about human reasoning. And if you ask what's the lesson of neural network machine translation, initially you might think that, machine translation, of all the tasks that people in AI considered, is the one that should be best for symbolic AI, because it's symbols in and it's symbols out, and linguists know lots about manipulating the symbols, at least they thought they did. But actually, if you want to make it work, symbols come in, you convert them into vectors inside, these vectors do things to each other, and eventually you turn it into symbols at the output. So you might think that's the end of symbolic AI. Actually, I think what it says is that symbolic AI was trying to use the wrong substrate. It was trying to do manipulations on symbol strings to get the work done. There's lots of insights about structure, but the bottom level substrate is these neural nets. And what you need to do is get your insights into the architecture or maybe the basic functions of the neural net and avoid all the work actually making it work. Let stochastic gradient descent train the neural net, but use your insights to decide what kinds of neurons we want, or things like looking for covariances rather than just weights times activities. Yeah. You can tell it's getting to the newer stuff because it's getting vague and the hand waving is getting more extreme. The last thing I'm going to talk about is something I've been working on for a while, which is computer vision. So for neural nets, what happened was there was a big win came from convolutional neural nets. And what a convolutional neural net does is say, if I'm going to have a feature detector that detects something at this part of the image, it's worth having a copy of the same feature detector that detects the same thing in another part of the image. That's called a convolutional neural net. And it allows you, for example, to learn something here and apply it over there. It makes learning much more efficient. And they've just wiped out other methods for computer vision. But they're doing the wrong thing. And so they work very well for object recognition, but they don't recognize objects the same way we do. And you can tell that because you can take an image of, say, a panda that's recognized by a neural net, and then you can say, can I change the pixels ever so slightly so that the neural net thinks it's an ostrich, but it still looks exactly like a panda to me? And you can. And that's pretty good evidence that the neural net's not recognizing pandas the way you are. You would never say this thing was an ostrich. It's still a panda. But the neural net thinks it's an ostrich. And the neural net is doing it far more by things like very fine textures, things that we're not really sensitive to and the neural net's using. It's a perfectly valid way to do it, given the training set. It will work, and it will generalize to new examples. It's just not the way we do it. I want to convince you that when we recognize objects, we do it by using coordinate frames, and by understanding the relationship between the coordinate frame of the whole object and the coordinate frames of the parts. And I try and convince you by giving you a task that shows just how dependent your spatial understanding is on coordinate frames. So most people think of coordinate frames as what you do when you do Cartesian geometry. You introduce those for doing geometry, but they're not how your mind works. I think Descartes' contribution to the mind was Cartesian coordinates, not all that linguistic stuff, or not that sort of dualism. And I'm going to convince you use Cartesian coordinates when you're doing understanding shapes. So, okay. Too much like that. Sitting squarely on the tabletop in front of you, there's a wireframe cube. It's about this big, and it's made of matte black wires. Here it is. And from your point of view, there's a front bottom left-hand corner here, and a top back right-hand corner here. Okay? And it's this wireframe cube. And I'm going to rotate it. I'm going to rotate it so this top back right-hand corner is vertically above the front bottom left-hand corner. So here's that diagonal that goes through the cube. And now what you have to do is put one finger, you have to actually do it. It's no good unless you do it. You have to put one finger on the book in front of you for where the bottom corner is. Put one finger for where the top corner is, assume the bottom corner is on your lap, and then just point in space to where the other corners are. Off you go. Just point in space to the other. It's a cube. How complicated could it be? You know what a cube is. So, what most people do, some people know this problem, but what most people do is say things like, well, here, 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 and here. And probably many of you will have pointed out the 4 other corners. And now imagine the cube in its normal orientation and count how many corners there are. There's 8, right? So if you pointed out 4 corners, it doesn't really matter where you put them, you're wrong. And it's not at all obvious to people where the corners are, because they think of where the bits of a cube are relative to its coordinate frame. And I forced you to use a different coordinate frame. And now you have no idea where the pieces are. Actually, there's 3 edges that come out at right angles like that, and then the 3 edges rotated 60 degrees that come out at right angles like that, and my fingertips are where the other corners are. It's like a benzene ring, it's a zigzag ring. And you can see the cube, right, and you can see that. You're thinking of a cube, and you're thinking of it relative to coordinate system. Okay, that's my evidence. There's lots more evidence. I got other evidence, which is computer graphics uses coordinate systems, and it has no trouble with viewpoint. And people have no trouble with viewpoint, therefore people use coordinate systems. That's what I call natural reasoning. So what we've done recently is used transformers to make a computer vision system that uses coordinate systems and can generalize better from less data. There's an archive paper that's not yet rejected by NIPS. And I call this Capsules 2009. I have a theory called capsules, and it's different every year. So a capsule is a group of neurons rather than an individual neuron. And it's a group of neurons that learns to represent a fragment of a shape. It's got a logistic unit that says whether it's present in the image or not. So that's just a binary unit. It's got a little matrix that says how it's related to how this shape is related to the camera. So to write down the entries in that matrix, you need to impose a coordinate frame on the fragment and say what's the relation between the coordinate frame of the camera and the coordinate frame of this fragment. And that can be written as a matrix, a transformation matrix. That's what that red square is. And then it's got various other activities like a vector of other activities like how deformed it is and what its velocity is and what its color is and stuff like that. So a capsule is going to have those 3 elements. And we're now going to try and train capsules, and we're going to train them unsupervised now. Previous methods have trained them supervised, in order to capture the intrinsic geometry. So if you think about an object, as I change viewpoint, the image changes a lot. But there's something that doesn't change as I change viewpoint, and that's the relationship between the whole object and a part of the object. That doesn't depend on my viewpoint. That's an intrinsic relationship. And that's where your knowledge of shape ought to be. It's not where it is in neural nets, but it's where current neural nets, but it's where it ought to be, because that's very robust. So we're going to try and learn an autoencoder. That is something that takes already discovered fragments. So that bottom layer is little capsules representing fragments you've discovered already, and tries to figure out which bigger fragments could explain those. So the bottom layer might contain, say, a nose and a mouth, and higher up you'd like to have a face as one of the high-level fragments that explains those low-level fragments. And what we're going to do is we're going to wire in a lot of knowledge into the model that predicts the parts from the whole. Now, that's not our real problem in perception. Our real problem in perception is we found some parts and we want to predict the whole, but we're going to leave that to transformers to deal with. For now, we're going to wire in knowledge of the generative model. This sounds like something someone might have said 50 years ago. And we're going to wire in knowledge about how a part is related to the whole. So if you know there's a face here, you know there should be a sort of mouth here. And so you know, because you know the relationship between the pose of the face and the pose of the mouth. And of course, if you change the camera, all of that changes, but the relationship doesn't change. So if you look here, this might be a nose and this might be a mouth, and this might be a face. And if you know the pose of the face, that's in this matrix here, and you know the relationship between a face and a mouth, that's in this green matrix here, which is weights, then you can predict the pose of the mouth. And so each of these higher level objects can predict the poses of where its parts would be. And for this already discovered part, which is a sort of little curve, horizontal curve, you might get predictions from various high-level capsules, and you're going to treat those predictions as a mixture model. That is, you're going to say, I don't add together all these predictions as I normally would in a neural network. I don't take all these top-down inputs and just add them up. What I do is I say they're separate predictions for what they should be, and what I need is that one of those predictions should be good. And if one of those predictions is good, and now we're going to train this whole system by saying I've got this magic transformer that looks at the parts I've already extracted, takes these existing parts, looks at all of them, and then tries to predict what wholes would explain those parts. And we tried programming this by hand and we couldn't do it very well, but a transformer can do it very nicely because it's very good at finding correlations between things because it's doing all these products of queries and keys. And it can predict what objects might be there and whether they exist and what their poses are. At least it could learn to do that if we gave it the right answer. But we don't know the right answer. But when we try and reconstruct these, we get an error for how well we explain these, and we can backpropagate the error up to here. And by backpropagating the reconstruction error, we can get a training signal to train this transformer. And hey presto, the whole thing works. I haven't explained it very well, but at least I conveyed the idea I'm still doing new stuff. That is, I'm still getting graduate students to do new stuff. Oops. And here's one little example of what it can do. You teach it about squares and triangles, and you teach it about squares and triangles not by telling it squares and triangles. You show it lots of images like this, right? You don't tell it about squares and triangles, you just show it lots of those. And an image is generated by taking a few squares and a few triangles and scaling them and rotating them and translating them and superimposing them. And all it gets to see is lots of data like that. But as a result of seeing data like this, it learns that there's these things called squares and triangles that can move around and dilate and rotate. And when you show it that, what it sees is this. So it sees, one capsule explains these 4 points, one capsule explains these 4 points, and one capsule explains these 3 points. And that's quite hard even for you to do. And it would be particularly hard for you to do if your training data was just images like that. So that's a toy example. We've also applied it to somewhat more realistic things, like Google has a whole bunch of house numbers that were got by its cars looking at house numbers. And we can train it unsupervised on all those house numbers, and it can do better than anything else at recognizing house numbers without ever having been shown labels. You basically train the representation with no supervision, and then just learn a model from the final representation to which number it is. and it's the sort of winner at present at that. So I'll just have a summary and then I'll finish only 1 minute late. My summary is, what we've really learned is that stochastic gradient descent can learn 1 billion weights if you give it enough data and enough compute power. Unsupervised learning is making a comeback. We don't really know what kinds of neurons we should be using or how they should be interacting. It's all up for grabs. So if you're a student, you shouldn't believe anything you hear. There could be very different kinds of neurons that work better. And in particular, there could be sort of vector nonlinearities, of which there are many, that work better than these scalar nonlinearities we're using. And what I believe, I used to believe naively that we should just forget symbolic AI. But actually, those people sort of thought a lot about the nature of the task and about evidence about how we do the task. And their problem was they were using the wrong substrate. And I think what should happen now is all that 50 years of acquired knowledge should be sort of redirected towards how do you get this kind of substrate to do that kind of processing. And I'm done.
Thank you very much. So now we have time for questions, and can I just remind the people who are in the overspill room that if you want to come and ask a question, you can come to the door, the adjoining door, and you'll be handed a microphone so you can ask a question that way. And for those of you who are here in the audience, if you put your hand up to get my attention to ask a question, if you just wait until a microphone comes to you, and it would be nice to just say who you are before you ask the question. So, any questions? Yep, a question just back here. That's great. Coming along to you now.
Thank you very much for the lecture. I'm Guido Sanguinetti from the University of Edinburgh. Your first question reminded me, I imagine it's intended, of Daniel Kahneman's Thinking Fast and Slow. And I'm not sure whether he would think that a system that only thinks fast is intelligent. And I was wondering whether you would want to comment about building large-scale infrastructure on something that captures just the fast thinking.
Okay, you try playing chess against AlphaZero when it's not doing any Monte Carlo rollout, and then you'll revise your opinion, because it'll wipe you out.
Well, but it's not just playing chess that we're trying to engineer.
No, I understand, but the point is, the sequential reasoning is very good at giving you a signal that allows you to get better intuitions, but you can do an awful lot with those kind of raw, direct intuitions. So a good diagnostician, for example, will look at a patient and say, oh, that patient has a bad heart or something. And then he tries to explain to the medical students why. You can do an awful lot with this direct reasoning. Now, of course, I agree with you that what's special about people is they use, and what gives us things like computers and bank accounts and politicians, is they can do reasoning. But I think what happened with symbolic AI is they tried to explain the reasoning without having this extremely powerful raw intuition in them. And now that we've got that, we can do things much better.
Thank you. Okay, so there's a question, a gentleman with the beard, yep, thank you.
Thank you. I'm Michael Herman from Informatics. So in this beautiful unicorn story, I was wondering how is it actually possible that there was some kind of coherency for a longer time? Why it didn't drift off to a completely different topic? Even I do this all the time.
Because it's a transformer which is looking at all the previous words and taking the current word and saying, how much attention should you pay to these previous things? So it doesn't forget the context. And it has actually, I think it was 10,000 or 1,000, I can't remember, probably 10,000 words. Now, you may say, well, there's no future in that because we can always go outside its memory. I have a whole lot to say about that, but I'm not going to say it now. You can get that memory for previous things either by just storing the previous vectors, or you could take those previous vectors and put them into an associative memory, and then use the query to access the associative memory. And that way you can put many more things in the associative memory than the dimension of the vector. And what will happen is when you'll get some interference, but that doesn't really matter that much for transformers.
Okay, David, back left there, thanks.
David Wallace, that was a fantastic talk. Thank you very much. The answer to the first question made me wonder whether machine learning will always be subject to unconscious bias, something that we have to guard against, the instinctive, rapid decision that we make on the basis often of prejudice. Any thoughts on that?
Yes, I mean, it's very good at being prejudiced, but I think it's probably easier to fix than people, because you can, for example, you freeze the weights, and now you can measure how it's biased, and you can measure who it's biased against, and you can try and correct for that. And there's also a whole field on how you can train it so that it's not biased in certain ways. You specify what it mustn't do, and you can train it so it doesn't do that. That's much harder to do with people. So I think it's true it's going to be biased like people are biased, but it's going to be much easier to fix these big neural nets than it is to fix people.
Was there a question over there? Yep, yep, you got it. Thanks.
There's a technique that was invented fairly recently called feature space, or the feature space of the data. So I'm going to ask how it works and how it's applied in neural networks.
Yeah, you got me. I don't know what that technique is.
It tries to find new features of the data that haven't been provided to it beforehand, and then basically provides a map of the data. How does that work, and how has it been applied?
I don't know about that technique, so I...
Okay. Anyway, and a question right at the back, and then I'll come down to you.
Hi, thank you for the great talk. You mentioned in some earlier interview that you think that we should abandon explainability, or like we shouldn't be thinking about explainability too much. But I was wondering, how can you trade off that with how are you going to go forward? Because without explainability, without understanding the systems, what is our heuristic for improving them?
Yeah, I strongly believe that politicians shouldn't legislate that you're not allowed to use a system unless you can explain how it works. Because these big neural nets, suppose they've learned 1 billion weights, and suppose what those billion weights are doing is capturing thousands upon thousands of weak regularities in the data. Some strong regularities, but lots and lots of weak regularities. And often when it makes a decision, it's that these 10,000 weak regularities suggested you should say yes, and these 5,000 suggested you should say no. So you say yes because there's more of those, or they're a bit stronger. And that's how it works. Well, if that's how it works, there's no way to say how it works that's simple. So I think a lot of politicians still believe that. They don't understand what these things are, and they think they must be computer programs. And if it's a computer program, it must be some instructions, and you must be able to say how it made a decision. Well, I think for these neural nets, you can't say how it made a decision any more economically for many of them than, look, here's the 1 billion weights, that's what it does. So I strongly believe that if politicians are allowed to say you can only use a system if you can explain how it works in the terms they think it ought to be explained in, that'll strongly inhibit us from using the best systems. However, I agree with you. We'd really like to understand how these things are working. And in order to make progress, you'd like to understand how you can make them work better. And so we desperately want to understand them. It's just we can't assume we're going to be able to.
And down at the front here, the second row from the front. Yeah.
Thank you very much for your talk. My name is Aaron Quigley. I was wondering if your current work is inspired by trying to make it more explainable, because
Yes.
the story you were telling us does have a narrative that does seem to make it explainable to people. And how would you encourage younger researchers to make the leap into doing things that are more explainable?
I don't know about younger researchers. I think probably the best thing that older researchers can do with younger researchers is provide funding for them and leave them alone. But Yeah, you're right. I don't like the way neural networks do object recognition at present, even though they're good at it. I strongly believe that there's all this evidence that we use coordinate frames and that we could get more statistically efficient object recognition. That is, you wouldn't have to train from all different viewpoints if we wired that in. So for convolutional nets, we know that wiring in translational equivariance is very powerful and helps a lot. And surely we can wire in a bit more than that, because we know a lot about what viewpoint does to things. And if we wired that in, the net should work better. And what's more, they'd be more explainable. The more explainable is the sort of side effect, but I'm really interested in getting them to be able to generalize from much less data. And I think if you can wire knowledge in, you should. It's just, we know that a lot of it's going to come from learning. And we have a few examples like convolutional nets where you add in a little bit of knowledge and it brought you a huge amount. There must be more like that. But yeah, I think, here's what I believe about old researchers and young researchers. Young researchers should read Max Planck. And Max Planck said, science progresses one funeral at a time.
Okay. Yeah, this gentleman on third row back, third in.
I'm not suggesting you should try and speed up the progress.
Thank you very much, first of all, for a wonderful talk. Michael Camilleri from the University of Edinburgh. You ended your talk talking about actually the need to combine symbolic reasoning with these connectionist networks. How do you envision that this can be done? Is it through changing some architectures, through changing the way the data is presented?
I don't really know, but let me give you one example. So if you look at transformer networks, they're coming up with a query that's being matched against keys that come from other words. And if you look at what I think of as symbolic AI, people studying language, there's something called categorical grammar, where you have things like verb phrase looking for a verb or something. I'm very sketchy on this. But it looks like that kind of thing should be going on in transformer networks. So it looks to me like, A, you'd like to see if that's what they're doing, if there's some of that going on, and B, if there is some of that going on, maybe you can use insights that come from that field to make them work better. So that would be one example. There's another example I'm interested in, which is how you do true recursion in a brain. Recursive call gets to use the same neurons and the same weights, and that means when the recursive call finishes, it needs to pop back to the higher level, and so all that information about what was going on at the higher level when you made this recursive call cannot be stored in neural activities, because those neurons were reused for the recursive call. So it has to be stored somewhere else. And I strongly believe there's fast wait memories. That is, there's associative memories that store short-term memory that allow you to do these pops. And I think what's going to happen is at present we've just had two timescales. We've had activities of neurons and weights that learn slowly. And those have been the two kinds of variables with just two timescales. Now, real synapses have many timescales. So I want to give each synapse several timescales so it can have long-term knowledge, but can also act as a temporary store in the weights. And then a query can do, instead of matching the query against keys of previous words, the keys of previous words could be used to store things in an associative memory in synapses. And then the query could be the input to that associative memory. And a query that's close to the key would produce the value that's close to what that key would have produced. So you can actually implement this business of a query matching a key and producing a value by saying, let's take those key value pairs and store them in an associative memory. So for all the previous words, we just have synapses that are storing these key value pairs, and then you access it with a query, and what you get out from that query is the sum of all of the values weighted by how well their keys matched, which is just what you want, except for the exponential, which screws things up. So that's one of the things I'm working on now. And I think we're going to have fast wait memories to be able to do temporary storage, to be able to do anything like real reasoning.
Okay, there's a question here, just straight in front of you, the row straight in front, 4 in. Yep, just that. Thank you. And I've got a threat for you, because I'm worried about the gender balance of the questioners here. So if I don't see any women asking questions, I'm afraid the molecular biologist will have to ask one, and you'll regret that. Anyway, for you.
Hello, I'm a PhD from University of Edinburgh, and I have a question. So as people, we can access our past memories to update our current actions.
Sorry, you'll have to talk slower because my hearing's not so good.
As people, we can access our past memories
Okay.
to update our current actions. In neural networks, they update based on what kind of current or an online experience. And we shift the kind of the past memories to optimization algorithms like ADAM or AdaGrad that accumulate gradients or something like that. So what is your suggestion?
Okay, so if you look at a recurrent net, and you want a recurrent net to have something that happened a long time ago, you want to take a gradient that you've got now and have it influence what you did a long time ago. You have to go back through many, many time steps, and that's crazy. You'd be much better off having what happened some time ago in an associative memory, using the current state to access the associative memory so that what happened a long time ago is now reactivated, and you're doing the learning not by backpropagating all through time, but by reactivating this past memory, and now you don't have to backpropagate through time. All you have to do is have this associative memory and use the current thing to reactivate the past thing, rather than going through all these steps. Because backpropagating through time just doesn't make sense for a brain.
So would you say those would be some sort of separate neural modules that contain past memories?
I'm not sure they're separate neural modules. I'd rather have it that every synapse has multiple timescales. And so you have a synapse that learns slowly, but it also has a component of the weight that learns fast but decays fast. And that can store temporary things.
Thank you.
Okay, and you've been saved. There's a question from Bonnie at the front.
I want to go back to the unicorn story where this system is using everything that it's learned about language and text and produce this story. And think of it in terms of the machine translation, where machine translation should be constrained by the source language. But it doesn't seem like this kind of system can distinguish the things that it's hallucinating from what it's learned, from what it's constrained to be mapping into the target language. And I'm just wondering, in the vision world, it would be like you see something, but your knowledge tells you, oh, there should be something there, and you hallucinate it. So I'm wondering if you could comment on hallucination.
Well, yeah, I mean, this thing has prior beliefs about what might come next. And if those prior beliefs are strong, they can overcome the data. Anything that uses priors is kind of like that. And it's a question, I think it's just a question of getting the balance right. I mean, and what I was showing was, you're lying to it all the time. You're saying guess, and then you're saying you were right, and then guess, you were right. And that's different from what you're doing in machine translation. Yeah.
Time for maybe one more question.
Preferably from a woman.
Would be good.
Even a molecular biologist.
Oh, okay then. So I've got two, but I'm sure you can dismiss both of them really quickly. So one of them is, you made a comment just back propagation, and you said that human brains don't work by back propagation, and if they did, would be a lot smarter.
Well, I'm very ambivalent about this, because back propagation is the right thing to do. And it'd be very surprising if evolution hadn't figured out the right thing to do. On the other hand, with only 1 billion weights, you can do this quite good translation. And 1 billion weights is just a tiny fraction of our brains. So I'm really confused.
Yeah, because I wondered if we could learn how to do back propagation, if we weren't, consciously.
I would have thought that it would be evolution that had evolved the back propagation algorithm. Okay. And then you use it for learning.
Okay.
And I would have thought there was lots of evolutionary pressure to evolve something that's equivalent to backdrop.
That would be, yeah.
And until fairly recently, I thought, the brains must be doing that. But then I realized that actually, once you start training a few billion parameters, they're sort of better than us. So it's not clear why. I used to want to explain how we're so intelligent. Now I want to explain how we're so stupid.
Okay, I quite like that. Maybe the very last thing then would be that we've invested a lot through European funding to fund a human brain project. And I wonder, given something like the Human Brain Project, whether you think the output, and there will be output from that, whether that will help or hinder what you do.
Well, definitely one or the other.
Okay, I think on that note, so what I would like to do is just to draw this to a close, but if you'll bear with me for just a couple of minutes. I can tell from the look on your faces that you, like me, have found this an absolutely wondrous lecture. It's been terrific, and whilst you were talking, and particularly, and there will be others like me in the audience for whom this is not their specialist subject, who found it so illuminating, but also the care that you've taken to explain it to people for whom this is not your living work to think about these things has been extraordinary, and it's meant a lot. Although I had a concern during the talk that it reminded me a little bit of, I used to listen when I went to the gym of podcasts of Richard Feynman, who was a particle physicist, and I used to listen to his lectures when I was exercising, and I used to rush home, and they were all magnificent and all understandable in the same way that you have been understandable. And then I used to go home kind of breathless, and it wasn't just from the exercise, it was because I was so excited about the Richard Feynman lectures that I'd been listening to. And I would go home to my husband and say, I've just been listening to this amazing lecture. It's all about... And then I wasn't quite able to explain how fantastic he was, and I think that might be part of my problem when I go home this evening, is not, I want to listen again and again to what you talked about. And we can do that because it will be on our YouTube channel. So we'll be able to go back and we'll be able to listen again to this, and I think it will be time well spent. It was fantastic. You gave lots of advice to, or how we should treat young researchers. I like that. We give them a lot of money and just tell them to get on with it. I think that's unsupervised learning, isn't it? Yeah. So this was really a tremendous treat, and for me, there's a sense of pride in this being the President's lecture that you've given this evening, and I think deep learning is safe in your hands. Please join me in thanking Professor Hinton.